Welcome to this lesson on study of linear algebra, and so this is gonna be on linearly independence and dependence. Right, so I'm going to use all these ideas to talk about bases and dimensions. So I wanted you to just know how to go about when we say linearly independence and dependence. All right, so the set S with vectors. So if you have a set S and you have some vectors in it, it's said to be linearly dependent. Okay, so the set is said to be linearly dependent. All right, so notice that if for distinct u1, u2, un, so you have distinct vectors in the S, there are scalars, so there are numbers. That's how you can think of it. Which not all AI is zero. What I mean is that it's not every number that you have here that is zero. Some of them might be zero, but then the whole idea here is not all of them should be zero. That is the whole case. Such that you can say that then the numbers multiplied by, a1, you have a number multiplied by the first vector u1 in S plus a number multiplied by the second vector all the way to whatever you can think of, sum up to zero. And notice that not all the AI, some of them are non-zero. So this is a very crucial point. Some of these are non-zero. Now, on the other hand, if all AI or if all these A's are supposed to be zero, so that the sum of these should be zero, I mean, when you have A1, U1 plus A2, and then remember, the A1s are numbers, the A's are numbers, and then the U's are vectors, right? So if you have A1, U1 plus A2, U2 plus the rest all the way to AN, UN is zero, with all of these being zero before you can get this condition, then we say that S is linearly independent. What this whole thing means is that assuming I have something like the numbers 3 and then 5, right? I have 3 and 5. I can say that if I do have 3 is 3 and half and 5 have some common multiple, right? So I can say that 3, let's assume that 3 is a vector. So I'm just looking at it in terms of numbers. If I write -5 in front of this 3 plus 3 in front of the 5, so here I'm just taking these as vectors. What would this be? This is going to give me 15, -15 plus 15, which is 0, right? So I'm able to get some scalars which are not 0 and then multiply them with 3 and 5 in such a way that when I sum them, I'm going to get 0. So the whole idea about linearly dependence is what it means. On the other hand, let's say I have these two numbers, 11, right? And maybe 11 and maybe 4. I don't know, maybe there might be numbers I can do, but I just come on. I just want to have some numbers and say that I cannot actually maybe 11 and maybe one half or a half. Okay, I know there are still numbers I can multiply to these two things that I can, but assuming there's no other number, then the only way we can do this will be 11, 0 plus 11, and then 0 times 1 half, and this is going to give me 0. And in this case, our A1 will be this, and our A2 will be 0, and all of them are 0 before you can get 0. That's what it means. It means that for you to get 0, or for you to have a linear combination of these to be 0, then all the scalars you are using in your linear combination should be 0 for the linearly independent part. But if you have the linear combination being 0, and all the scalars are not 0, not all of them are 0, then you have linearly dependent. So in this case, you can have some of them being 0, some not being 0. But here it's very necessary that you get all the scalars to be 0. Now let's look at this. I have these two set, and I want to check if this is linearly independent or dependent. So the first, how you do this is sometimes you can use what we call row reduce echelon form. I'm going to do that with these example, and then you're going to understand that. Okay, so what you're going to do is set some equation, some scalar a1 maybe times the first vector you have here, so you can call this u1 and u2, plus some scalar, maybe you can call it a2. Let me use those kind of scalars, so that you get it, you get to understand it very well. Okay, a1 times our u1, and that is u1 is 1 1, plus a2 times our u2, which is that. And I want to check if this is linearly dependent or independent. So what is going to happen is, after doing this, all of them should give, like, the linearly dependent and independent, my target is to get 0, so I have to equate it to 0 and check whether these scalars should be different numbers or maybe they should be, zeros. So I have a1 times that, I'm going to have a1 and a1 again, and plus negative a2 again. This should give me 0, 0 0. And in the first equation, I'm going to have a1 minus a2 equals 0, equation 1. I'm going to have a1 plus a2 equals 0, equation 2. This is a straightforward, how do I call it, simultaneous equation that I can do. So what I did was I just summed the first entry, so this guy plus that guy, and you sum the second entries as well. But I'm not going to add them to get, a very simple simultaneous equation and the rest. But what I'm going to do is I'm going to take what we call row reduce echelon form. So what you're going to do is you write the numbers, you have your coefficients here. A1 in front of A1, they are just 1 1. You write them as a column, and you put it in one matrix like that, and you write the coefficient you have here, which is negative 1, and you write the coefficient you have here, which is 1. It's 1, but we don't write, so that's why you have a1, a2 there. You multiply it by the variable you're talking about, and this should give you the 0 vector. And you're going to reduce this guy, and when you reduce it, that's what we call the row reduce echelon form. And again, I chose this method because if you just compare this to the set you have here, you realize that the first column is just these first value entries of first vectors, and the second column contains it. So maybe in the next problem, I'm going to just write the vectors I have straight away in the columns of the matrix. Right? So what we are going to do is form an augmented matrix, which is 1 negative 1 and then 1 1, and then you bring some parallel lines like this and bring your vector that you have at the right end, which is 0 0, somewhere here. In this problem, if you don't bring it, there's no issue, but there are some problems that's going to demand that. So the way you reduce this is make sure that you start with the leading value of the first row, and that is 1. So I'm going to write everything in the first row again, and on the other hand I have 0. Now make sure that the leading value in the first row, which is 1, the value below it is 0. So what you're going to do is compare this to what common factor do they have. So if I multiply, there's this value and this value are the same, right? So I can just subtract them. So what you're going to do is do row 1 minus row 2 should be our next row 2. So our next row 2 is row 1 minus row 2, this guy. So always stand on what you're looking at minus the next one you want to reduce. So I have 0. So this value minus that value, I'm going to get 0. And I go to negative 1 minus 2. Minus 1. And that's going to give me negative 2. Then I'm going to have 0 here. Right. Yeah, I'm going to have that 0 there. So what you're going to get here is I really want to make sure that this is working. All right, so so yeah, I'm gonna have, what this whole thing means is that we are going to now multiply this reduced matrix negative 2. You can divide through by negative 2 by our variables a1 a2, and then equate it to whatever we had here. So ideally we are supposed to subtract these two as well, but if you subtract 0 and 0, you get that. So I'm going to continue here. Now with this means that if I do a matrix multiplication between this matrix and this vector, I'm going to have a1 minus a2 equals this one, 0 here, and I'm going to have this guy times a1, and that's going to give me 0 a1. So I don't write, I'm going to have negative a2 should be equal to 0, and this implies that a2 should be equal to 0 from here. And if a2 is 0, then a1 is also equal to what? A2 from here you can make A1 the subject, and you're gonna have A1 to also be equal to what? 0. So what this whole thing is telling us is that it means these two vectors, or these two vectors, you have u1 and then u2 in this set S, is actually linearly independent. Alright, so that's what it means. It means that since we've been able to say that a1 times the first vector time plus a2 times the second vector is equal to 0 vector, and after solving it, you could also solve it from here. Like I said, you can use very straightforward simultaneous equation. Add these two equations, you're going to get 2a1 equals 0, mean a1 is 0, and then a2 will be 0 as well. So it means that these two values that we've gotten for the scalars, I mean a1 and a2, are zeros, and that is the only option giving us this linear combination to be 0. So that means this set is linearly dependent. All right, yeah, it's linearly dependent because when you have a1 into the first one plus a2 into the second one equals 0, I mean the 0 vector, let me write it well. This is only possible when a1 and a2 are both 0. And on the other hand, we had s to be equal to 1 0 and then 0 1, and this is linearly independent as well. Like I've seen it before, so it's just linearly independent. But you can also do it that way. So you have that plus a2, which is 0 1, and that should give me 0. So I'm going to look for values such that I'll get zeros here, and they're going to give me a1 0 0 a2 and 0. And then what I'm going to do is I sum the ones I have here, a1 plus 0, which is a1 and is equal to 0. I sum these two, I'm going to have a2 to be 0. So this set is also what? Linearly dependent. There are some sets that are not linearly dependent though, but an example of that is when you have s to be equal to maybe 1 1 and 2 2. Right, so this is not linearly dependent. Why? Because you have a1 into 1 1. I wanted to just give you an example of that. Maybe a2 into 2 2 equals 0. What I'm going to get is a1 plus 2a2, then a1 plus 2a2 again. This is 0, this is 0, right? And if you do matrix, the matrix you get will be a1 2 1 2, and then you reduce it with this 0 0's argument as well. And if I go to the next page, I'm going to have 1 2. This is where you get to appreciate why I said use matrix. Okay, I mean, if I reduce it, I'm going to make sure that the leading element you have here, which is 1, has below it 0. So I just have to subtract these two numbers to get 0. So if I subtract these two, I'm going to have 0 as well. So what you do for the first one, you do for all the other rows. Then I subtract 0 and 0, I'm going to have 0 0 there. So it means I'm going to have 1 2 0 0 multiplying a1 a2 should give me 0. After reducing, you use your reduced matrix to continue again. Now the first row is saying that a1 plus 2a2 should give me 0, and I'm going to have a1 to be equal to negative 2a2, and this is the only solution we have. And what this is telling us is that whatever a2 I choose, a1 should be negative 2 of a2. Now look at, I had the set to be 1 1 2 2, right? This is the set I had. If I choose a2 to be, let's say, 1, this is telling us that a1 should be equal to negative 2 times a1, so that would be negative 2. And so I'll have a1 is negative 2 1 1 plus a2, which is 1 into 2 2, and indeed if you sum this, you're going to get 0 0. You can also choose other options. You can choose a2 to be, so in this case you always have to choose a2 because a1 is always negative 2 of a2. Again, you can choose zeros, but this is telling us that we have other non-zero scalars that can produce 0. I mean, when their linear combinations will give you 0, which the scalars we have are non-zero. I mean, I don't know if this makes sense, but that's what it means to be linearly dependent and linearly independent. So in our next discussion, I'm going to talk about basis, which is the main focus of this class. All right, thank you.